Hi, everyone. We're going to do a shear and moment diagram problem. And we're going to start here with, now before we get to our internal shear and moment diagrams, we've got to get our global reactions. So I'll create a little free body just above for that purpose. So we free the body from the supports. I'm going to put A sub y and B sub y here. And I'm going to need a resultant force equal to 3 times 4 is 12 kilonewtons. I'm going to have a couple moment of 24 kilonewtons times meters. And then I have a 9 kilonewton force over. And I'm going to, thinking ahead, I'm going to do a moment summation about A. So I want to find out how far away each one of these is from this will be my moment arms. So I'll need that one, that one. Hey, the 12 kilonewtons is half of 4, so that one is just 2 meters. To get to the 9 kilonewtons, that looks like 8, 4 plus 4. And between A and B is 4 times 3 or 12. With all that in mind, we are ready to do our moment equation. So summation of moments about A is equal to 0, counterclockwise positive. Assume B sub y is upward. First term, 12 times 2 negative. Next term, 24 negative. Next term, 9 times 8 negative. Last term, B sub y positive, and moment arm of 12. Okay. And we can run that through your calculator. I have it pre-solved. We get a positive 10 kilonewtons, and that confirms our assumption that that force is upward. We also need to solve for A sub y, so let's sum forces in the y direction, set it equal to 0, upwards positive. So I'm going to say AY plus 10. Those are the two things pointing upward. Have to balance with 12 plus 9. And let's see. 9 is 11, so A sub y is 11 kilonewtons. So we get a positive sign. So that also confirms our assumption that A sub y is upward. Now that we have our reactions, we can put them here. I'm going to remove the support and replace it with its effect on the body. So at A, we had said 11. And B, we had said 10. We can just clean that up a little bit. All right, time to do our shear and moment diagrams. I'm going to label the plots and give them some units. And I'm going to adjust my screen. I can see the plot and my calculator simultaneously. Looks pretty good. My shear diagram starts at 0, it ends at 0, and we're just going to follow the direction of the arrows. So we're going to increase by 11 suddenly. We're going to decrease by the area under the curve. It gets me to -1. My loading function was constant, so my shear function, when I integrate that, needs to be linear. And linear means I connect the dots, straight line. Okay, Here remains constant until I get to my next load. So I decrease by 9. Then when I get to the extreme end of the beam, I increase back by 10, and that gets me back to 0. But my shear diagram is looking really good. So if you are taking statics with me or mechanics of materials, I'll ask you to label all of your functions so that I can double check and make sure you know which are constant, linear, quadratic, et cetera, et cetera. All right, moving forward into the moment diagram. So we are noticing that we have an applied moment here. So what I'm going to do is, right when I get to this point in the moment diagram, I'm going to remind myself that I'm going to have to jump. There's going to be some type of discontinuity there. And the other piece of information that I need is when I go to do these areas of the shear diagram, I'm going to need to know these dimensions in order to get those areas of those different triangles. So this one's going to be 11 divided by 3. That's because the slope is 3 kilonewtons per meter. That is the slope. We know the rise is 11. And so 11 divided by 3 is the run. Okay. And same thing here. So this one is 1, which is the rise, divided by the slope of 3, which of course we can read directly off of the loading plot there. So 11/3 and 1/3. Okay, we are ready to go. Start at 0. And we increase by the area of the first triangle. Whoop. I didn't think it was going to do that. We want to increase by the area of the first triangle. And so it has a height of 11. It has a base of 11/3 and multiply by half because it's a triangle. And that's going to bring us up to 20.2. And I'm going to go ahead and construct a little construction line here just so kind of we know where we're at. And I'm going to put it about here. All right, so since the moment diagram is our quote unquote final answer for this problem, we want it to be to 3 sig figs. So 20.2 is fine for reporting answers, but keep in mind that that's only okay as long as you're tracking that 4th sig fig somewhere else. My calculator has them all. So I'm going to continue to use my calculator as we move throughout the curve. Okay, let's do the rest of the points, and then we'll come back and put in the functions last. So now we need a negative area right there. So we're going to subtract. And we want the base of the height of the triangle, which is 1, the base of the triangle, which is 1/3, and then multiply by half because it's a triangle. And now we're going to get to a nice even 20. Right there. 20 is okay, 20.0 also okay. I'm ambivalent whether or not you show the 0.0 or not, doesn't matter. Okay, now I've gotten to this little yellow area that I'd identified beforehand, which is just my reminder to myself that when I get to this point in the plot, don't forget that I have a discontinuity, a jump in my bending moment. And this is the part that, static students get so mad about this, but basically clockwise, jump up, counterclockwise means we jump down. I'm not going to take the time to explain why this is in this particular video. I have that in other videos and texts and examples. So for now, we're going to take that at face value and say that that applied moment is clockwise. Therefore, we're going to jump up or increase by 24. So let's add 24 to my running moment summation that I'm doing over on the left. 20 plus 24 gets me up to 44. All right, now we have a nice rectangle. So our next move is to decrease by 1 times 4 is 4. That gets me to 40. And then our last area under the shear curve is a rectangle. It's 4 by 10, which is 40. It's below the 0, so we subtract 40 and we get back to 0. We don't get back to 0 on our moment diagram, it means we have an error somewhere to find. It could be in the shear diagram, it could be a calculator error, it could even be an error on your reactions. Okay, great, looking good here. So now it's time to fill in the functions, flesh those out. So we have linear shear, and that means we're going to need a quadratic moment. And then a constant shear integrates to linear. Okay. For the first segment of the beam, the values are decreasing from left to right. Therefore, my moment function is concave down quadratic. And these are these very subtle, smooth. Oh, that one really sucked. Let's try that again. These are these subtle, smooth parabolas. So something like that. In terms of communicating your work on homework or an exam, it doesn't hurt to just kind of put that symbol there. So quadratic concave down. And that way, if I'm your teacher, right, if I'm your professor, if I'm assessing your work, I don't have to micromanage your curve and make sure that it's clear. There's annotation. I can kind of give you a little bit of a benefit of a doubt there. All right, for the rest, I just need linear functions. These are my favorite easy ones. Connect the dots, maybe with a larger pen. And that is it for my moment function. Good. Boop, boop. There we go. Shear moment diagrams. Hip, hip, hooray. That's the end of the video. See you next time.